So hello. So the third speaker of the session is Jeremiah Birrell from the University of Massachusetts Amherst. So take it away.
All right. Well, thank you very much for this opportunity to speak. So I'm going to talk about a class of so-called divergences, which are capable of interpolating between Wasserstein metrics and f-Divergences, and hope to convince you why these are interesting things and useful things to look at. So this is joint work with several people: Paul Dupuy, Marcos Katsalakis, Yanis Pantazis, and Luc Rabelais. And first, let me kind of give you a big picture of the type of thing that that we're interested in. So the general problem is one of approximating or learning a model. And by model, I mean probability measure. So thought of as finding an optimal fit or optimal approximation in some sense. So the setting is you have a quote unquote true model Q, so either analytically given or from data. So my talk will have more statistical bend to it, but you can also use it in certain analytical situations. And then you have some class of approximating models, P, and you have some means of determining what you mean by optimal or best fit. So here, the mathematical setting is that of a divergence. So this is a weakening of the notion of a metric. So it's a map that takes two probability measures, gives you a non-negative number, and it's 0 if and only if Q equals P. And so the fitting or approximation problem is to solve for the best fit, so the model in your approximating family that minimizes the divergence between the true model and the approximation. So there's lots of interesting problems that can be phrased this way. The classical one being maximum likelihood, also mean field theory, variational inference, and generative adversarial networks. So that's the application I'll highlight later on. So just one classical example, as I mentioned, maximum likelihood. If you have a parametric family, P theta, and IID samples from Q, then maximum likelihood is equivalent to a relative entropy minimization problem. So relative entropy is maybe the most classical divergence that isn't a metric, and minimizing that is equivalent to maximum likelihood. And the choice of divergence has a large impact on properties and performance of any given method. So I'm going to talk about a class of divergences that interpolate between two very common families of divergences. And so let me first introduce those. Particularly, what is most useful, especially in data-driven applications, are divergences that are defined via a variational representation. So what do I mean by that? Well, you have an objective functional constructed out of expectations under your two models and some space of test functions. And the divergence is defined by optimizing over the space of test functions, the objective functional. So classical example are f-Divergences defined by some convex function on the real line. And this is the objective functional. I won't talk too much about the details of it, but the key things to note is Q and P only show up through expectations of various functions, and then you optimize over the test function space, here bounded continuous functions on a metric space. So KL divergence, otherwise known as relative entropy, is probably the most classical example, and it fits under this. In that case, this becomes the Donsker-Varadon variational formula. Alpha divergences, another very useful class, and there's lots of different ones, but these are the ones that I'll mention here. And then the other family of divergences, this case metrics, that are very useful in many applications are Wasserstein. So here, the objective functional is just difference in expectations, and the test function space are bounded one Lipschitz functions. So a comparison of these two, different classes. What are some strengths and weaknesses? Well, Wasserstein depends on the geometry. So it can be thought of as a mass transport cost. It can be finite, in other words, informative, even if the measures are mutually singular. So that's a very useful property in many situations. A drawback is it's often infinite in the presence of heavy tails. So one of the main motivations of this work is to adapt these kind of things to a heavy tail setting. In contrast, f-divergences essentially have the reverse of these properties. So they don't depend on the geometry at all. They measure mass redistribution cost. They're uninformative in the mutually singular case, but they're much better equipped to handle heavy-tailed distributions. So the goal here is to construct divergences and prove properties about them that interpolate between these two cases and show they inherit useful properties from both. So the class that we study here are what we call the f-gamma divergences. And essentially they use the objective functional from the f-divergence, but restrict to some other space of test functions. So some space in some subspace of the space of bounded continuous functions, or specifically some convex subset, but I won't get into exactly what assumptions we make on gamma here. The analog of Wasserstein in this more general case would be what are called integral probability metrics. So again, the objective functional is just a difference in expectations, and you take the soup over some test function space. So these are the two things that we, this is the generalization of Wasserstein, and the claim is that these f-gamma divergences interpolate between the f-divergences and these integral probability metrics. So just summarize the main results in this preprint here. So the first is one sense in which we have this interpolation. So you can show that the f-gamma divergence is an infimal convolution of an f-divergence and an integral probability metric, so like Wasserstein. In particular, the f-gamma divergence is bounded above by both the f-divergence and the integral probability metric. So this tells you that it's going to inherit a lot of the nice properties from both of them. So it can be finite and informative when the measures are mutually singular. It can be finite in heavy-tailed cases where Wasserstein alone is not. Critically, for it to make sense as a discrepancy, as a tool for quantifying discrepancy between measures, it needs to have the divergence property. So under suitable assumptions on f and the test function space, it is. So it's non-negative and it's 0 if and only if q equals p. And another sense in which it interpolates between the f-divergences and the integral probability metrics is if you scale the test function space and send that scaling either to infinity, in which case you obtain the f-divergence, or to 0, along with this 1 over delta rescaling of the divergence, you arrive at the integral probability metric. So as I hope to demonstrate, the fact that the f-gamma divergences inherit these properties from both subcases are extremely useful in applications. First, let me just mention something that will help, hopefully help give a little bit more of an intuitive idea of what these f-gamma divergences are doing. So one other thing that we showed is that the infimal convolution formula generally has a unique solution. And so this is, gives a interpretation of the f-gamma divergences as a two-step process in which the first step, the measure p, is transformed into gamma star, the intermediate step, by redistributing mass. And you pay an associated cost given by the f-gamma or the f-divergence, which one way of expressing that is through the likelihood ratio. And so this cost only depends on how much relative mass you're redistributing at every point. It doesn't depend on how far you move the mass or anything like that. So first you pay a redistribution cost, and then in the second step, you go from the intermediate to Q, paying a cost equal to the integral probability metric. So in particular, in the Wasserstein case, this is a mass transport cost. So in the second step, mass is transported from gamma star to Q as the final step. So the fact that we incorporate both of these steps gives the F gamma divergence is a lot of power that either of the components individually do not possess. So let me use the rest of my time to talk about a very useful application of divergences with variational representations in general, and specifically these F gamma divergences. So in general, a divergence that has a variational representation is extremely useful in a data-driven setting because the objective functional, well, it only involves expectations of things. So you can estimate it using IID samples from the two measures. So specifically, the log likelihood does not need to be estimated, which is a really good thing because that's extremely hard to do in very high dimensions. And we're specifically interested in higher dimensional applications. So in particular, for the F gamma divergences, we can use these to construct generative adversarial networks. So this is a specific instance of this learning task that I introduced at the beginning, where you have some divergence between a true exact measure and some family of approximating measures, and you want to minimize that. In the F gamma divergence case, it looks like this. This is a min-max problem where you have an objective functional just involving expectations. So again, you can estimate this from data. Now, by generative adversarial network, I mean a specific machine learning framework, which is essentially how you parameterize your approximating family p theta. So in that case, you take some noise source X, so maybe a high dimensional Gaussian, and you push it through some neural network family, so called the generator. So this is some neural network family depending on some parameters theta, and this is how you get your distribution, your approximating family of distributions. And then you also approximate your family of test functions by another neural network called the discriminator. And this min-max problem can be approximated via stochastic gradient descent. You can think of it as a two-player game between these two networks, the generator and the discriminator. And in this case, you can approximate your model that's generating your data Q to high accuracy. And this is a very useful paradigm that is very successful. So let me just show you the results of one numerical simulation that illustrates the benefits of the F gamma divergences over each of them individually. So here, the measure generating the data is heavy-tailed. It's a mixture of 4 two-dimensional t distributions that are embedded in a plane in 10 dimensions. So this top block of figures shows the projection onto the embedding plane, and this bottom row is regarding the components perpendicular to the plane. So in the first step, or in the first block of figures, we showed samples from the generator. So essentially what we've learned about the model after a certain number of epochs of learning. So as we go across horizontally here, we've done more training. Each row is for a different choice of F in the F divergence. So illustrating that different ones can perform better than others. But you can see here as we go through towards here 4,000 epochs, this choice of F especially has learned the lower dimensional projection pretty well. And then if we look at the components perpendicular to the plane, we can see that as we go through more and more epochs, these are peaking. very close to the support plane of the distributions, which is here just at 0. So the F gamma divergences perform quite well here. The F
let me interrupt you. So we're sort of out of time.
Okay.
But are you done mostly?
Basically, the only thing left to say is this last plot here is for the Wasserstein, using just the Wasserstein metric, and it fails completely. Instead of peaking around the plane, it spreads out over the full space. And so it fails in this heavy-tailed scenario. So thank you, and sorry I went over.
Okay. So let me stop the recording.